First thing first, I think there's a good chance that I won't be traveling on April 7th. So likely I won't be traveling, but I guess there will be no class still. But we can likely do some meetings on projects that should be more helpful. We'll see. I mean, I'm still waiting for the some clearance letter from India government, but it doesn't seem like it will happen soon. So there's a good chance that I won't be traveling on that week. But we'll likely just do, project, meeting to get some progress on that week. And, that we're supposed to be, for you to work on your project. So that's the same idea. Cool. And other than that, we don't have homework. It should be up soon, just to fill up the 10 points left. But it shouldn't be too tricky compared to the previous homeworks. Not too technical intense. Cool. Other than that, yeah, just keep in mind that we sort of have 1 month left before the project presentation. So keep that in mind and plan accordingly. Cool. I guess we can just continue. Today we are jumping into the, I guess, more technical thing, but it's technical because that's something we are now using. So, most of the music generation, or I don't know, if you go online and all the new startups, they are basically using this so-called latent-based generation thing. So that's something we will talk about today. But before that, I think there's still one thing we haven't finished for the audio domain music generation, which is DDSP. And I bet you will be very interested in this because it's pretty cool. So last week, on Monday, we talked about some of the thing about, audio domain generation. Of course, we started with, discussion on AI song contest. But at the end, we were talking about, audio generation, and we were talking about one specific thing is the vocoder. So which is the model that we use to go from, spectrogram. That's mechanical only spectrogram, and go in from that to back to the waveform. So, that's technically not, so generation as you might think, because it's, you have male spectrogram, or, have the spectrogram, you pretty much have 80% of it. So you're just filling the details. Cool. So this is another, important model that sort of like redefine what DSP is. So, DSP stand for digital signal processing. So, it's just the traditional way how we deal with signals. So we consider audio as signals, and we apply mostly, double E techniques to synthesize or analyze audio signals, basically. And that's some of the old, not old, I mean, still being used. Some of the traditional synthesizer are using. So all the keyboards you see, or, if max MSP, that MSP sort of just stand for signal processing in some sense. So, the whole idea of signal processing is, going from simple sine wave, can you synthesize something, just changing different components and modulating stuff, and try to see if you can get a synthesizer out of it. But also the other side is that how do you analyze stuff? So differentiable DSP is just sort of like challenging that idea. Can we sort of like make it into a deep learning immersion? So by deep learning is that, we want it to be differentiable. Somehow stuck. So the idea of DSP is, combining both analysis plus synthesis. So it's basically something, sort of like a codec, or sort of like the autoencoder that we talk about. It's, thinking about a way to decompose some input audio signal into certain different, dimension, and we want to turn it back. So the core idea, the easy way to look at it is that you get some audio. Think about these audio, not the, very long, complex audio. This is like monophonic, single instrument audio. So, you have some encoder to get the F0. So this could be done, as we said, we know some of the, pitch estimation or F0 estimation model. So this is a deep learning model. And you also extract the loudness. This is much easier because this is just, compute, root mean square, compute, maybe just magnitude and try to figure out how loud that is. And that basically is a function of the magnitude of the signal. But basically, you can easily get like a number or, a curve that represent, think about it like ADSR for the audio signal. And F0 is, the fundamental frequency. So what he wants to do is that, once we extract this two information, they're thinking about, can we go from this and back to restore the original signal? So now you have F0. You can think about it, can we add that, timbre information back to it? So harmonic audio is that. So, looking at the input audio, can we extract some of the timbre characteristic? And then we will restore that harmonic part. So, F0, but 2 times F0, 3 times F0, 4 times F0. What's the ratio between those harmonics? And there's also filter noise. We will see it later. But basically, this is the good old, additive synthesis model is working on. We have those things that's harmonic, and we have some of the noise that just inharmonic. But that would be, think about guitar playing, there are fret noise. Think about flute playing, then, you will have that, like airflow sound. So all kind of those sounds is not harmonic. But anyway, you add it back and then you get the reverb, you get the synthesis audio. So the tricky part is here, there's this hidden Z. So as you realize that from F0 and loudness, there's no way the model can realize how to, faithfully recover the whole signal. So, you somehow, if you want to see what this timbre is like, if you get F0 and loudness, there's no way you can tell whether it's a guitar or it's a flute. So this Z thing is basically, sort of like extracting some of the useful information from the target audio, but basically think about it like extracting the spectrum of the audio. So, if it's a flute, you get some spectrum, look at, how these, F0 to F0, what's the ratio between them. And for guitar, you extract some of the other thing. But that's the information that's passed from the input. And to train it, it's just an autoencoder. Cool. This should give you a better sense what it is. So this is the original audio. And there's no sound. Let me see. Yeah. So this is the input sound. So, you first do an encoder, you get the fundamental frequency. Let's listen to it again. Cool. Let's do it again. So you have the F0, that's the pitch you listen to, and the loudness is just like how loud it is over time. Yep. So you have both these information as the input for the decoder. So what you want to get are these three things. So first you get the amplitude. So this is sort of like trying to mimic this, but this is much easier, just the waveform amplitude. And harmonic distribution is basically, again, sort of like spectrum. So how many, I don't know, how much stuff in the lower frequency side and the higher frequency side. So you can look at this and, it's sort of like similar in the sense that, how harmonic distribute over different spectrum. And then noise magnitude is the additive, the noise, filter noise part. We will see it later. So with these two, you can get this additive audio. So basically is, just frequency plus loudness. So this is what you get, just like perfect sinusoid wave, and then you just add them up. So there's no noise. There's, and the other part will take care of all those, fret noise, or, like the how you bowing, then you get some noise. This is what it sounds like. It sounds kind of funny, but when you add them up, this is what you get. So those are, the noise that give you that, realness of it. Let's listen to it again. This is the original, pure sine waves. Oops. And this is what we want without reverb. And this is the thing that added to it, mostly at the attacked part. That's, the characteristic sound of violins timbre. You can think about it just like, when you're bowing, that, that some not vibration, friction, or, all those tiny sounds that it made that contribute to it. And finally, you just add the reverb back, and hopefully it will be similar to the input. And this is the reverb. So, that's basically how this thing works. So this thing just corresponds to this thing. So the whole idea is that, you figured out a way to train this model. You want to train this encoder and this decoder. There's additional Z somewhere here. But anyway, the idea is that can we extract these information so that it can faithfully reconstruct the original sound? And initially, everything will be really bad. I mean, they use pre-trained pitch estimation, so this would be good. Loudness is much easy, pretty good. But the decoder at first is just generating random stuff. But over the time, because the whole process is differentiable, so you can go all the way back to train this model. And over the time, it will just improve. And this is sort of like at the end what you get. So, this is cool because, if you look at the way how they do it is that, you get some audio, and you can extract F0, and you can extract the loudness. And in addition, you also get the Z. So this Z sort of like control what timbre is. So, you grab a guitar sound, you get a guitar Z. You get a flute, you get a flute Z. So that's sort of, that Z is the thing that you can sort of like characterize what the timbre for a specific instrument is. And then if you pair with different F0 and loudness, you sort of like disentangle different dimension of a sound. So that's actually what tone transfer is based on. And also, tone transfer is using, Hanoi's song on that P9 tuning. We can listen to it again.
Hey, it's your boy Hanoi, and this is how to make AI-based music from Thailand.
So, basically that's how they do it. They grab the P9 recording, and you can extract F0, and you can extract the loudness, and you get that Z. So now once you do it, you can sort of like, two ways to do it is like, one is like, you grab another sound, and then you can play with P9, but it sounds like a different sound. Because you use your P9 audio, you get an F0, you get a loudness, and then you swap the Z with another instrument. But more interestingly is another way is like, can you just play the original, instrument that you know how to do it? You can play violin, you can play piano, you can play, guitar, but can it sounds like another instrument? So that's the whole point of tone transfer. But, that can be enabled by DSP in some sense. There are some links that you can play with, but, that's DDS. Cool. And if you want to dig into how these things work, generating music in a waveform domain, it's a much harder path, but people have been exploring how to do it for a while. This is like 2020, so at the time people are looking into how to do it. Cool. So let's jump into what we want to do today. That's the latent-based audio generation. Any question on the PDSP? Yeah.
So the last step between the combined and the full synthesis is like just adding reverb.
Yeah, it's just add the two thing together and then add the reverb. So there are tons of limitation here. So first is that the reverb is fixed. So it's sort of like assuming the whole data set is just one single reverb. So if you look at their data set, how they train it is, the same, same violin being recorded and, all different tones and different things, but it's the same recorded environment. But that's how they train it. So reverb is not part of it. So if you send some other audio, it will just get the clean sound out of it. But that's how they train it. They have two versions. I think this is I think they have like two versions of the data set. One is like using NSYNC. So NSYNC doesn't have any reverb, as you know, in homework 2. And this is the violin data set they have, but this one does have reverb. So for the NSYNC one, you can think about it like, yeah, there's no reverb at all. Yeah, so you're asking this, right? So just add these together and this step, there's a reverb. That's it. Yeah. And that reverb is fixed for this particular data set. So there are some limitations, but in general, the idea is, to think about, can we sort of like decompose an audio into interpretable components and mimic the whole way of, additive synthesis. The filter noise is, also that's the subtractive synthesis. So this is additive synthesis. So you get a bunch of sine wave with different frequency, different magnitude, and add them together. That's what you can get. And this is subtractive synthesis. So that basically means that you get a white noise, and then you just filter by this noise magnitude. So that's, part of the, high frequency part, you want to get rid of it. Lower frequency part, you want to get rid of it. But these are the frequency being that you sort of like remain, you want to keep in the output noise. And that's, filter noise. So, these are all good old good old DSP way of synthesizing sound. Cool.
So the harmonic distribution aspect, that's just learned from training, right? Like none of that, like that information isn't encoded into the.
It was not here, but it was here.
Okay.
So it actually goes through the other side. It should be Z here.
Okay.
Somehow I didn't put it here. But the Z would be used to get OD3s. So amplitude should be much easier to get from this. But noise magnitudes would also require part of the Z, because if it's a violin, you get a lot of attack noise. If it's guitar, it's like fret noise. If it's flute, it's airflow noise. So it's different noise.
Okay.
Yeah. So that would be in the Z. So that's something missing here. So harmonic distribution somehow correlated to the F0, because it will depends on F0, but the actual ratio depends on the input sound. So this Z is sort of like, whoops, where is this? Sort of like capture all the information about the timbre. Yeah. And that's the funny part, and you can sort of like think about it like turn from a piano sound to guitar gradually, just by changing the Z gradually. I think they have some result that you can check, but you can do all sort of thing just playing with that, Z. That's the latent space thing that we will be talking about next. But that's the interesting part of latent space is that, you know, you get some lower dimension thing and you can just play with it and you will get, you know, that sort of like continuous morphing sound. That's impossible if you're doing waveform. If you get to waveform and do interpolation, it just sounds terrible.
So is that essentially what the plugin is doing when it's like, because it's like it's tone transfer. So like when you enter it in like like you singing or something, then it just takes the note and then like kind of adds the timbre of the
Yeah. I think the plugin will give you basically that free thing like F0 and I never use that, but that's what the model will generate, you know, F0 and the loudness, and there's some Z. That's just a vector.
Right.
Yeah. So that's the three things you can play with. So think about it, you know, get the same F0, but with different, you know, loudness curve, the same loudness curve of different F0, or you play with timbre. Tone transfer is playing with timbre basically. But you can think about other, you know, way of doing it. Maybe you can use your hand to control the loudness instead of, you know, using some input thing. So all sort of thing. If you can get that F0 and loudness and some timbre, then you can recreate, sort of like get a VST basically.
Okay.
Yeah. Cool. Let's dig into this. So latent-based music generation. It will be very kind of tough, but we'll see. But this is, you know, what's being used in some of the commercial. I don't know whether they are earning money, but at least those are the commercial thing that we have today. So get a sense what those are. But you know, lots of it is, you know, still undergoing, you know, development, and things just change over the time. Cool. We'll just skip this. So last week we were basically talking about, you know, audio synthesis, and 2 weeks ago we were still talking about symbolic music generation. But you know, that's far from, you know, you know, some of the legal things going on. Some of these big companies that they are just generating that, you know, good sounding, like good fidelity audio, and somehow generating some music that people are afraid of, you know, copying the training data. So what are those models are about? This is what we want to figure out today. Cool. So we start from this neural codec thing. I think we talked about it a little bit. Did we? Likely not. So cool. So what is a codec? Basically, you know, a codec is just how you transfer audio file between different device. So you know, likely if you're using earbuds or, you know, any Bluetooth headphones, then that's essentially what's going on under the hood. So you want to send out audio from your smartphone to your headphone, and it's not transmitting those, you know, waveform, because it doesn't make much sense if you transmit like that, because the bit rate or, you know, the bandwidth just doesn't support that. So usually you might have heard some of these, you know, SBC, AAC, aptX, you know, LDAC. But that's, you know, something you can choose when you are, you know, connecting to your, you know, Bluetooth earbuds or headphones. But basically, you know, under the hood, it's sort of like encoding those audio into some other format and, you know, send it to the headphone. But you know, if you're doing Zoom meeting, that's the same thing. At the same time, you have a bunch of video. So these video, well, you know, think about MP4, MOV, MKV. So all different format of video. They are all also some kind of codec, because the idea is that can we turn these video into some, you know, compressed format, and then you can send to the cloud so that you can send it to others. And this include also, you know, microphone, so that you send to the cloud and people will receive it. So, you know, everything in between is, you know, some other format of your original audio that's being sent to your, you know, peers. So, that's how traditional codec is about. So, think about it, codec is just, it's not only just MP3 file. It's like, well, if you encode it and then store on your, laptop, then it's sort of like a file. But if you are doing it on the fly, then that's another way to think about codec. But basically, codec is just that, taking some audio, you have some encoder, turn it into some other format that's more compressed and much more, data efficient, and then you decode it back. But nowadays we're living in this neural era. So, the idea is just simple, neural codec basically just turn everything into a neural network. So what you want to do is, you want to train a neural encoder and a neural decoder that can, turn the audio back. And how do you train it? And these two will be some neural network. How do you train it? The same idea, just reconstruction. And, from time to time, you'll realize, reconstruction is just the only choice that we can do. So lots of this training paradigm, we start from, classification where we have pair data. So we have label data. But when you are doing generation, usually there's not many choice. If you want to recreate the original sound, that's the only way you can do it, just through reconstruction. So you will see a lot of model are just using reconstruction loss as their training loss. Cool. We'll likely skip this part, but just give it a sense, now the codec world is actually undergoing some, major change. So lots of the codec are actually being replaced by neural network. And, some of your earbuds is actually using neural network to transmit the codec, even though it's happening very slowly. So at some point, MP3 will not be MP3 anymore. There will be, some neural component inside it. But it has to be, run decently well on different devices. But at some point, we will see something like that. But these are some of the early model. We won't go into detail, but you can see, encoder, convolution. But basically, this is just a huge convolutional network, and decoder, again, same huge convolutional neural network, but just in the other way. So on one hand, you go from waveform at 20K kilohertz and all the way down to some, compressed embedding at a much lower sampling rate. So, this is like one single value at 24 kilohertz. So 24,000 sampling for each second. But at the end, you get some embedding. Maybe that's, just 64 or 32 beats per sample, but you are in a much lower frequency sampling rate. Anyway, we will go into detail of these, but think about it just like a good old autoencoder. So this should be a much better view of that. So you have some audio, you turn it into encoder, and you turn it into a very tiny representation that you can send over to other device, and you want to decode it back. And so they also use this discriminator, sort of the same idea of GM, so that you can compare these two. But in addition to that, you can also use reconstruction loss to train it. So, at the end of the day, what you want to do is that you have an audio, you take the encoder and you turn it into some, signals. And you send the signals to the decoder. So at the receiver side, think about it like at your phone, you have the encoder. So you know how to turn, waveform into a bunch of 0, 1. And then you send those 0, 1 that's much smaller in size. You send it to your earbuds, and in your earbuds, you have the decoder that will decode that back to the waveform. So, think about it like this way, is like in the old time is that, transmission is the bottleneck. So we just send the whole waveform. Think about the old school, landline transmission for audio, then just send the original audio and then you just play it back. But this is a different way. We try to realize, try to figure out a way that can compress the audio into a much compact format. Anyway, we will go into detail of these, but there are different versions of it. But anyway, these are all just codec. Cool. I'll skip this. Cool, but that's basically just give you a sense. We can look into some of the example, I guess. Just give you a sense, you know, nowadays these codec are really good. Well, I don't think we will hear any difference here, but let's see. So this is the original music sample. So this is the encodec. That's the previous version of their this model is trying to do. This is there. So they are in 8 kbps, and they compare to another neural codec that's 24 kbps. And this is what I can do with 8 kbps. Think about 8 kbps. It's crazy good. A typical think about a typical MP3 file is like 3 megabytes per 3 minutes. So usually it's like 1 megabytes per minute, and this is just 8 kilobytes per second. So sort of like good enough as sort of like MP3-ish, but it's real time. So, you likely need a better headphone to see the difference, but, they go from 24 kilo BPS to 8 kbps. That's pretty impressive. So, now people are still trying to push that limit, but, pretty much all you need to know is that, nowadays these codec are working very nice. And you can think about it just like a neural version of MP3 codec, and things are getting mature. Cool. Cool. So let's dig into this latent diffusion models. So we've talked about this autoencoder a little bit, but all the encodecs, the codec thing, and all the even DDSP is sort of the same idea. You go from something and then you turn it into some lower dimension thing, and you wanna train that decoder and to put it back. So here would be the encoder, and at the in the middle, this would be the bottleneck layer, which is much smaller than the input layer, and then you use the decoder to turn it back. And how you train it is basically, well, these two has to be the same. So think about codec, then the input waveform after encoding and decoding. You should get something pretty much similar, pretty much the same as your inputs. And in DDSP is the same idea. You have the input, you extract F0, extract loudness, extract some hidden Z, and at the end, what you want to get is that after all those DSP thing, you get some audio, and that audio should be similar to your input. So pretty much DDSP and the thing we just look at, codec, are both autoencoders. And we've talked about this when we talk about diffusion models. The idea is that, if you get some image and you train an outgoing encoder, if you don't do something fancy, usually they will just get rid of all the details, because, Lee is something that just happened once in your data set. The model will be like, well, I don't want to waste my, bandwidth to encode these, detailed information. So usually what you get is something blurred, but at least it got the same idea, the same shape. So this is the sort of like the core of the whole latent diffusion model. So what I want to do, you can just think about this VQVAE just a fancy way to do autoencoder. But basically what I want to do is add additional vector quantization into the VAE thing. So there's some complexity, but let's just move on. Cool. So the whole idea of vector quantization is that, we have some latent Z space. We don't want the model to just, use whatever those are. We can use just a fixed number of vectors to be used. Cool. So this will be the key of understanding latent space diffusion model. Well, again, today it will be very, very technical intense, but, sort of get an idea. And get to see some of the interesting component in this latent diffusion model. And I guess the idea is to see how complex it is. You know, and in the future, whenever people talk about these models, you get a sense that, you know, it's not just diffusion model, it's not just GN, it's not just VAE, it's sort of a mix of everything. So this is like VQGM. So this is the first time sort of like people realize you can just use this VAE plus GN thing to generate very high quality image. So how to do it is that, you know, you take an image and you turn it using a CNN encoder to turn it into some, you know, hidden things. So you can think about this as just like MP3. So you have an image, you go through some encoder, you get a bunch of numbers. Those numbers are the thing that you store in an MP3 file, and then you decode it back. So the key reason why this is working so well is that it actually adds a discriminator at the end. And this discriminator is different from the discriminator we know in GN. Now this is doing this patch discriminator thing. So it's actually looking into, you know, the tiny chunk. It's not looking at this whole image and say whether this is a dot, but rather it's like doing this, you know, tiny chunk and see whether these are good images. So it's not, you know, just detecting whether it's a dot, but rather, you know, looking at each single tiny patch. So in this case, it's like 16 patches. So look at each single patch. Are there, you know, weird stuff going on? And, you know, this discriminator's goal is not to detect whether this is a dot, but rather whether each single patch look like an image. So that's the core idea. With this discriminator, you can improve the quality and sharpness of the output because, you know, it will be looking into the detail. Does this fur direction match with one another? Does the nose have all those, you know, detailed texture? So those are the things that this discriminator is looking at. And, you know, the high level structure will be handled by the encoder and decoder. Cool, we would just get rid of this. But basically what you can get is something like this. So, you know, it's the first time people can do this high resolution thing. I don't know how big this is, but likely 2000 times 8000-ish. So, but it's crazy big. So this is the first time people realize, you know, you can just use this kind of generated model to get such, you know, high resolution stuff. So the reason why they can do this high resolution is that, you know, we have this encoder decoder thing that's handling the high level thing, but at the same time, there's the discriminator that looking into, you know, tiny patch of each single thing. So think about that. GN is not like, well, does this whole image look like an image, but rather, you know, just zoom in and see whether this is like a good image and looking into this, whether it's like a good image. And through just scanning through the whole image with that discriminator, it will sort of like make sure all of the details of the whole image will be realistic in some sense. So that's the whole idea of latent diffusion model. You try to sort of like do a collaboration with two models. You have some very high level model that's usually some VAE thing, but you have the GN to handle the very low detailed thing. So with this VQGN, people can do all sort of cool stuff. You know, they can also do this kind of thing that, you know, you have a depth map and you can synthesize new images based on that. You can also deblur. You can also go from, this is like sketch-ish thing, back to the original image. And you can also do semantic map. So you have, you know, sea, lake, glass or wood, and sky, and turn it back to the some new image. Cool. So that lead us to this latent diffusion model. So this is basically what latent diffusion model is in their original figure, which is very tricky to see. But basically what you get is first this VQGN thing, that's the autoencoder. But you can think about it just a fancy MP3. So you have some audio, you turn it into some other representation that's much more compressed. And, you know, once you have MP3, then that's it. now we are generating stuff as MP3 bytes. So the whole idea of latent diffusion model, the latent, meaning that, now we are no longer generating audio in the waveform domain. We are generating audio in MP3 encoded strings. So that's the whole idea of latent diffusion model. And that MP3 encoder is not MP3 encoder, but it's some other, neural code that we talk about. But basically the idea is that, well, it's very challenging to, use WaveNet to generate audio just like one by one sample. But if it's like, think about it like MP3 encoded streams, then maybe we got a chance to do it. So latent diffusion model is just one type of that. So, you see the VQGN, they are actually using transformer to generate those, beats within that MP3 codec. But latent diffusion model is just using diffusion model to generate those MP3 streams. Cool. And pretty much that's it. So, all of these, crazy stuff is just the same, diffusion model that but just turn it into a different way. So, you have Z here is what you want to get. So, you have some audio, you turn it into some Z, and you go through the diffusion process. So remember, recall that diffusion model is going from an image and you add noise for 1,000 steps. So this diffusion process go from, a clean image and then add noise for 1,000 steps, and then you get something pure noise. And what you want at the end when you are generating stuff is going from a noise and then remove that noise for 1,000 steps. So this is like one single step. It's a UNet, but it's just a model that will remove that noise. And you do this for, T-1 plus this time. So, you do it for 1,000 times to get rid of all the stuff. So that's pretty much just latent diffusion model. So you can think about it as a diffusion model, not working on, pixels, not working on waveforms, not working on spectrograms, but rather it work on, some latent space. By latent space, it means some, sort of like MP3 or some codec space of your input signals. So that's pretty much what latent diffusion model is. And it's very hard to visualize those because, you are not generating the original signal. You are generating something you don't know what that is. So you are generating some MP3 codes, basically. That's the idea. And there's additional complexity. You can actually add more condition to that, but this is just through some conditioning. If you have the data, if you have some data to, we call it condition the model, but basically it's like controlling what the model to generate, then you can add it through this. Anyway, we can just look at some examples. So these are latent diffusion model, the first time, I guess, not the first time. I mean, people can generate this even before latent diffusion model. But, just once again, showcase how good these latent diffusion model are. So these are sort of like if you have used Mid-Journey or Stable Diffusion. I forgot what's the name. Stable Diffusion? Yeah, Stable Diffusion, Mid-Journey, they sort of have the same era of these. So, the reason why it's called Stable Diffusion is because they are using latent diffusion. And latent diffusion is much more stable than the original diffusion model. That's why they called it latent diffusion. Anyway, you can also do this. You have, sky, you have, I don't know what these are, this likely mountains. And you can generate different version of it by just sending this semantic map. So you can think about it, this is a good way to control your model that, you can generate different stuff. Cool. So I guess, even though it seems quite technical, intense, but, this is just a summary slide. So what latent diffusion model is actually a chimera. There's a neural codec. And think about it like an MP3. So you have some codec that turn in some audio into some other representation. That's where we call it latent space. So in this case, and CNN-based autoencoder trained with GN like adversarial laws, but who cares? People will use different things. Maybe in the future, people will be using other stuff, train with different laws, but the core idea is the same. You want to turn, audio into some MP3 streams rather than doing stuff on audio. And you have this diffusion model working on that latent space. So you are not generating the waveform directly. You are generating the MP3 beats. And you have a conditional module so that you have transformer-like cross attention mechanism so that you can control what you want to generate. And, there's also GN hidden here. That's, the adversarial loss. So, you can think about it. The data diffusion model is just everything. You have GN, you have CNN, you have transformer, you have autoencoder, you have diffusion model, you have UNet, pretty much everywhere. You also have ResNet somewhere. So this is the correct way to look into latent diffusion model is that people always think about, latent diffusion model somehow it's just a diffusion model, but it's not. It's just everything. So you have, GN, you have a diversity loss in the codec, and in codec you're using CNN, and it's pretty much a UNet, and you are using an autoencoder to train that codec. And within the diffusion model, you have a UNet in each single speed, each single step out of that 1,000 step, and you have transformer to do all the conditioning. Questions? Kind of too intense? Yeah.
In the image that's generated,
Mm-hmm.
while it did look realistic overall, the reflections in the water looked very wrong.
Very wrong. Mm-hmm.
How are there techniques for like making sure there's cohesion across the different patches?
You mentioned a good point. It's like, they basically have like two layers of it, VAE, like the autoencoder, get image and then decompose it and then get the image back. So, the reflection is actually much harder than, tiny patch because the GM patch doesn't cover that. So if you wanted to do it the correct way is that you want a GN, discriminator to look at, this and this like reflection, does it match? But, the GN patch that you slide through it is usually smaller than that. So it's very hard to get those. But if you look at the lake boundary, where the boundary is, it actually is pretty good at that region. But the further away, the harder, because that's where there is no communication or no GN discriminator to look at those. What kind of model are you looking at? I feel like many of the model they do a really good job on where you have the at the boundary part. So if you look at this, it's not exactly the same, but if you look at previously, it's pretty bad. So this is actually doing a much better job currently, but it's not perfect because when you are doing, let's find a better bigger things. This is the first type they generate. So these are pretty bad because there's not this thing, but I think the boundary somewhere here. So it's really bad, but at least it's sort of like trying hard to recover it. But that's VQGN. That's not the latent diffusion model. But now we have latent diffusion model. Then you look at this. These are reflection. It doesn't match, but at least for these part, it tried hard to match. And these is sort of like, I think it's doing hard. At least at the boundary is doing the right thing. But the further away, there's little chance that the model will get it right. Like this, it's too far away, and your discriminator patch would be just this size, so it never covered this size. If it's this size, then GN can provide signal for it to know that it's not a good reflector. So that's the complexity and the technical challenge. But for now, I would say at least at the boundary, people are pretty happy about what we can get for now. And usually reflection is the most challenging one to get it right. And 3 years ago, people are always talking about the hand thing, like neural network never get the hands right. It would generate 6 hands, 4 hands, or in maybe 2 thumbs, or just the model just couldn't capture the distribution well, and the model doesn't have the ability to count. So, in general, those are the technical challenge, and it's still not solved, but it's getting better. Yeah, that's how I can say. And technically, that's the reason why it's very hard for the model to do it, because that GN discriminator patch just doesn't cover the whole reflection. And there's no way the model will try hard to have that, long-term relationship, that reflection, but it's pretty hard for the model to do it. Yeah. Cool. And some of the new video generation model, they are also pretty good at capturing some of the, CG challenge. So I would say, it's improving over time, but still there's tons of artifacts for now. Cool. I guess this is the slide that you want to sort of have a sense on, rather than, all the details we talk about. But basically, the model we were talking about, latent diffusion model, all these, stable diffusion, mid-journey for image, or, Suno for video, or, for music and audio. It's like, all these like music gen, audio gen, and, music LM, and I don't know, like Suno, likely, we don't know what that is. But stable audio, all these models are sort of based on the same idea that it's a mix of everything, but at least it should be running in some neural codec space. That's where we code it latent space, rather than just generating waveform or spectrogram directly. Cool. So, we can look into some of the latent-based audio synthesis model. So we talk about, pretty much in the image space, but, the audio synthesis is the same idea. You have waveform, you use two, neural net to turn it into something else. So this is the neural codec. And what you want to do is, you want to generate something in that space. So this is the whole latent-based audio synthesis. Usually you have a pair of encoder and decoder that turn waveform into some other latent space. That's what we call it, latent space. And then you go from some random distribution and you try to generate some, you want to train some generator that generates stuff in that latent space. And again, everything here are neural networks. So this is a typical step if you want to get a sense how people nowadays do these stuff. So first you train an autoencoder. So think about it, train a neural version of MP3. So you want to turn some audio into some, MP3 data stream that's very compact, but you turn it back with the decoder. So you train this, and you grab a bunch of different audio, and hopefully after you train this, they will give a different version, and those will be the same as the input. So you train it. So we add a fire here, meaning that it's training. So now what you get in the second step is that you compute a bunch of latent vectors from the audio that you have. And now we are not training it. We just, test this model. So you grab, this is where, all the training thing going on. So you collect a bunch of data, collect, millions of songs, and then you grab all the latent vectors out from it. Yeah, somehow animation pretty bad, but you get millions of songs, you get all the latent vectors. So pretty much after this step, the waveform are just gone. They just turn into, some MP3 files or, some latent space representation, just a vector basically. So these vectors represent the original waveform or a matrix. So now what you want to do is train this latent generated model. So, think about latent diffusion model is this. So you go from some random distribution, you train this generator that will generate those, cool, tiny MP3 file, basically. So you can generate a bunch of those. And at the end, once you generate these, you decode the latent vector that you generate with the decoder back to the audio waveform. So that's the whole idea of latent diffusion model. So think about it this way, is that, you are no longer generating stuff in the waveform or spectrogram, anything we know what it is. But now you are, taking some audio files, turn that into MP3, and look at all the the bytes, the 10 of that MP3, and try to generate in that space, because that space is just smaller and much easier to handle. That's the idea. So the whole idea of doing this is just 4 steps: train an autoencoder, and then grab a bunch of files, compute what they are in the latent space. Those are vectors or matrices, and you train a latent generated model to generate those latent vectors and matrices. And then at the end, once you generate those, you turn that back to waveform so that you can listen to. So in terms of training, there's just 2 things. So that's why, people always talk about codec and latent diffusion model nowadays. So codec will determine the how good this representation is. So, how good your MP3 or its, AAC, it's different codec, how good that is. But at the other hand, you also want to get a very good generated model to generate those encoded version of stuff. And when you are doing the generation, what you get is just this, you grab some random vector and you use that generator to generate, different version of it. And then you use the decoder to turn it back to waveform. So this is the way how whenever you run, Music Gen, Audio Gen, Suno, Music LM, this is what happened under the hood. You grab some seed, so random seed, you get a random vector, and then you go through the generator, you get some vectors, and then all those vectors will be sent to decoder to get the final waveform out. Cool. And so, we were talking about waveform, but it's pretty much the same when you are doing spectrogram. But with spectrogram, again, you have to turn spectrogram back to waveform, but that's also fine. So some of the model are actually not waveform based, they are spectrogram based, but the idea is the same. Cool. So we can look into some of the example of like audio gen. This is pretty much the first model that people try to generate audio. This is the model architecture. But we can take a closer look of it. So again, these are tons of technical details, but just grab some, idea of what's going on. So audio gen pretty much follow the same, latent generation approach. So, first we train this audio decoder and encoder. So, you turn this audio into some audio tokens. So these are sort of like, think about like MP3 language. So, you have some audio and you turn it into a bunch of words in some other space. And now, you take this and then you expand it. What you want to do is that, you do know what this audio is about in your training data. This audio is about a dog is barking in the park. So now your goal is going from this, a dog is barking in the park, to this audio tokens. So think about this audio tokens as some alien language that you want to generate. And this is the input language, in good English. So, this is pretty much just like a machine translation task. So you go from something you understand, English, to some, alien language you don't understand. But who cares? Those are alien language, and you'll know some way to turn it back to waveform. So, this is just a translation translation task. And, translation, as we talk about, transformer is proposed for translation rather than the GPT thing. So that's what they did. So they basically trained a transformer model to do it. But think about it like a translation model. And if you have good enough data, that's 4K hours for their case. It's crazy large at that time. Now people are using even larger data set, but 4K hours of speech, music, and sound effects. And what you want to do is going from, some, English text and turn it into alien tokens. But those alien tokens can be decoded back to the waveform. Cool. So any question on this? The high level idea, how it works? So again, the idea is going from some text, and your goal is to translate them into some MP3 tokens. That's the way you think about it. And you know how to decode MP3 back to waveform. So that's the idea. And seems very brutal force, but that's how they do it the first time. So this is audio gen. And if you know music gen, it's basically the same model, just applied to more music, basically. So this first version, 4K hours of speech, music, sound effects, this is what they can get. This is the input text. Well, I don't think they have any music assembled today. Yeah, but anyway, this is audio gen. You know, music gen, there's a Hugging Face you can play with, or this. Where's the Hugging Face? But anyway, you can search for music gen, and there's this Hugging Face. You can play with it. Sometimes it doesn't work. Shall we do something here? Any idea? On baseline. I doubt we can do it, but that's it. Okay, it's not working. Is it working? Oh yeah, it is working. It takes some more time, so that's when we can keep talking. So you know, music gen is basically the same idea of audio gen, and it is specific, you know, in codec. That's the one of the codec we talk about, but you know, it just keep improving. So anyway, there's some neural codec. That's all you need to know. And in this case, it's much crazier. It's like 20K hours of licensed music. So in this case, the reason why they can publish it is that because it's licensed music. They actually purchase the right to use that for training. So the internal data set is high quality private, but from my understanding, those are likely more, you know, stock music like. And Shutterstock, that's another stock music place. So they also bought like 25K of those, just instrument only. So anyway, these are the music they sort of like purchase, but mostly not the music that you listen to, but more, you know, stock music that's being used to, you know, create those YouTube videos that you can get. Let's see. I doubt we can do that, but that's it. Okay. Is it missing a beat or something? Anyway. Yeah. So, you know, there are different challenge here. It's like I think the thing is that it just doesn't understand the text. So, you know, in your model, likely you have, you know, in your training data, likely you have all those, just that you don't have good enough, you know, text and audio so that you learn some of the correlation. Yeah.
She knows about different genres, because that doesn't sound like something.
Yeah, I mean, so I would say pretty bad.
Yeah.
Yeah, but this is music gen. And when was that? It's like 2023 new riffs, so which basically means May 2023, so 2 years ago. And you know, at that time, there's just not a thing, to be honest. That's the first time, you know, after music gen, all these startups just pop up because they are like, okay, now is the time we think we can commercialize it in some sense, you know. Regardless of all those, you know, legal issue, that's when the time, you know, the industry started to be sort of like serious about this. It's like, well, you know, from the legal side, it's like, well, now this seems like it has the chance to actually copy the training data. But, you know, for, you know, commercial, you know, like startup industry, they are like, well, this is the first time we could potentially commercial this. And sort of that's where everything just started blowing up. So, you know, music gen is sort of at that era, the start of this. So it was not good, but this sort of like the baseline of all these stuff that we have today. Cool. So likely if you play with some of the other models, they do much better in understanding the text, but also generating the sound that correspond to the text. So that's much harder. And MusicGen is a very brutal force model. So we can look at a much elegant model, which is Music LM. But by elegant doesn't mean that MusicGen doesn't make any sense. It's like this is the first model, so that's how they did it. And it's very brutal force, but it shows that we can do it. So that's the contribution of that. So this is a much not much newer, but pretty much the same year, 2023. So pretty much the same year. Somehow I mess up. But Music LM, but it's much elegant, but at the same time it's much more complex. So anyway, it has three components: audio autoencoder, semantic representation. Just forget about what it is, but the key is this: text music correspondence. So that is the Mulan thing. That's improving the whole idea of how you know what this audio is versus this text. So it has trained a model that just go from this audio, the music, and rock song with distorted guitar. So it has much better annotation in their training data, and they specifically train this model. I guess we can just go over this and we will code it today. So this Mulan thing is actually the key component of Music LM, and that's why going from MusicGen that doesn't really capture how we understand text and how they correspond to all the different music features. And Mulan is the step toward that. Can we get better alignment between the text you send and the audio that you listen to? So it's using this thing called contrastive language image pre-training. Clip, that's for image. Again, lots of stuff come from image space and then later being adapted to audio space. It's just because, image community is 10 times, or I say 50 times or 100 times larger than audio field. Anyway, this is clip, how we train it, what we want to get. This is details about how we train this model, but get a sense of it. It's not too crazy. So clip is a pair of encoders. So you have an image encoder, you have a text encoder. It's a pair of encoders. That's one of the biggest, trick of this. So you take, you have an image cat, and then you have the text CAT. So you go through the image encoder, you get some representation, that's a vector. And then you have the cat CAT, you go through some text encoder, you get the embedding of that. So basically a vector of that. So what you want is that these two should be close, right? That's the goal of what we want. So you want to figure out a pair of image encoder and text encoder that somehow knows how to put the image and cat to the same space. But that doesn't actually get what we want. So now if we have a dog image and the text, DOG, and you can go through it and again get an image encoded version of the image, and you also get the encoded version of the text DOG. So the idea is that we want to make close these things. So the image goes through this encoder, it will get something closer to DOG going through this text encoder. That's the key point. But at the same time, we want to make everything further away. So we don't want the image of cat and the image of dog to be thrown to the same space. We want them to be further apart. And that's the name of contrastive coming from. So the whole idea of clip, contrastive language image pre-training, is using this way to sort of train this pair of encoder that sort of like shared a semantic understanding of image and text. So how does that play into this Music LM? So basically they train something similar for music. So think about it like, you have audio. This is audio, pretend it is. So some rock song or, maybe, funky bass line. So you have that sound, correct, funky bass line, and you have the text funky bass line. And you train pretty much the same idea. You have a bunch of music, you have a bunch of, annotation for those music samples, then you train this model. So after training this model, you sort of get a sense, how to interpret or, you know, how to align the text to the music. So for music LM, how it does is that, you know, you grab a bunch of audio. And first you go through this Mulan audio encoder. So you get this Mulan tokens that's going from the audio purely. So you don't have the text in this case. And how you do is that you generate a more detailed version of it. This is sort of the complexity of music LM, but think about it as just another you know, MP3 encoder, lower level, but, you know, something in between MP3 and the waveform. And again, taken with this Mulan and the MP3 codec, you generate the actual, say, FLAC, F-L-A-C, you know, FLAC, you know, lossless codec. So there are 3 stages. So first you generate, you know, go from Mulan, you generate something that's like MP3, and then you use the Mulan token plus the MP3 to generate something FLAC that's, you know, more detail and more information, more lossless kind of. You know, and then train on 5 million songs to 80K hours, crazy. But that's what you get as music LM. So how you do it is that during inference time, because you have this Mulan model that, as we said, you know, dog image and the OG map to the same space. So now you actually text something like hip hop song with violin solo. Even this text, you can still use this Mulan model to map it to some embedding. And that vector is actually close to the song that's having that thing. So you can go from that to generate the MP3 stuff and then pretty much do the same thing. Use the Mulan token plus the MP3 token to generate the FLAC and then going back to the audio. So, you know, this is what music LM is. We can listen to it. What you get is something like this. You know, look at the caption, it's much richer. Cool. Reggae and electronic dance music. And this like rising synths playing a arpeggio with a lot of reverb. Cool. You can play with it, but I guess the easier way is through this Music FX. This is the link. So if you're interested, you can play with it. You can just, you know, do something and generate something. This is kind of boring. It's like, well, what's the point of doing this? But the Music FX DJ, we will talk about it next week, but this is something more interesting. There's some coming from. It's not from this. Anyway, we'll talk about it the next week. So they create a very cool thing that you can sort of like change between different. You can sort of like. So you can just like morph between genre, like a DJ-ish, and you know, now lower classical, more metal. Pretty bad, but I mean, maybe that's too far away. But you know, if you do it correctly, you can actually morph from one genre to another smoothly. You know, if you're interested, look at Jekyll Collier, how he do something cool. Anyway, we could finish that next week. But you know, that's pretty much what some of the state-of-the-art stuff that you can do. Now they have a bunch of other stuff, you know, image FX, video FX, music FX. That's what we were talking about. Cool. Sorry for the very technical lesson, but that's the complexity. Embrace the complexity.